Okay, so let's talk about problem 3 on the worksheet, another Ferris wheel problem. Let's just write down some of the information we're given. We know that t equals, that's the period of the Ferris wheel. It makes 1 revolution every 12 seconds. And so our angular velocity, omega, equals 360 degrees divided by 12, and that equals 30 degrees per second. Okay, so that means that Francesca, after 4 seconds, is up here, because she's gone a total of 120 degrees, right? 4 seconds times 30 degrees per second. But for our purposes, we now think of her at a new time zero. This is Francesca at time 0. She's at 30 degrees compared to our standard coordinate system with the origin here at the center of the Ferris wheel. But when we, and that's, that's when we think in terms of x prime, y prime here, but we're going to change coordinate systems to x and y with our origin down here. And you all know this. You drew the diagram. I'm just reviewing the setup of the problem. So now we can come up with parametric equations for Francesca. And that's simply going to be, remember, that's x equals r cosine theta. And r is 20 feet. So it's r times cosine, and here's the only tricky part. Our starting value for theta is 30 degrees at time 0, so it's 30 degrees plus 30 degrees times t. That's going to be the angle after t seconds. So that's her x coordinate. And then y equals, okay, we have to, again, x equals x prime, that's no problem. Y equals y prime plus 26. So it's 26 plus sine of 30 degrees. That's the position at time 0. Plus 30 degrees times t. So those are her parametric equations. And then we've got Arturo over here. He's at 6 feet. And so he throws the ball 60 feet per second. So the x is going to be, the distance here was 75 feet. So 75 plus 60 feet per second times cosine of 120 degrees. And the y equals, it's a plus sign, 6 plus 60 times sine 120 degrees, and then gravity minus 16 t squared. So those are our parametric equations. Now, in this case, they don't, I guess you could do it the same way as problem 65 and find the minimum distance. Maybe that's the probably the best way to do it. Find the minimum distance. So use the same equation. Again, this is x1, x2, x1, y1, and x2, y2. Another way to solve that would be when does x1 and x2, when are x1 and x2 equal? Well, you can make this term, or this side of the equation equal this side of the second equation for x, or x1 and x2. And if you make those equal, then just simply solve for t in the first pair of equations, and then plug t in here, and I guess that's everywhere. Plug t into the y equations and find out how close y1 and y2 are to each other when x1 equals x2. This is just another way of thinking about the problem, but the better solution is to do the minimum distance. So dt equals the square root of x1 minus x2 squared plus y1 plus y2 squared.